Okay, let me present the third part of my lecture. We will discuss here the methods for the identification of the charge hadrons. Since the interactions of charge hadrons are rather similar, the most direct way to distinguish them is to determine the mass. The momentum of charged particles is measured by the tracking system, so determining the mass of the particle is equivalent to determining the velocity of the particle, since momentum is known. If you know velocity, you could determine mass, as is obvious from all these formulas. There are four main processes that depends on the velocity of a particle, and we will discuss these four processes in turn. First, most direct is to measure the time of flight, or TOF, of the particles over a fixed distance. Second method, we can look at the detail of the interaction of charged particles with matter. The main source here is the energy lost via ionization, which depends on velocity. Thirdly, if the velocity of the particle changes compared to the local speed of light, then it will radiate photons known as transition radiation photons. And finally, if a particle travels at greater than the local speed of light, it will radiate Cherenkov radiation. So time of light. The simple concept is to measure the time difference between two detectors' planes separated by the distance d. Then the velocity of the particle in the units of the c is given by beta, and beta is equal to d divided by c dt, where the t is the time of the particle travel. At high energy, particle speeds are all relativistic, and they closely approach speed of the light. Hence, for a 10 GeV kaon, the time to travel 12 meters, which is, I would say, maximum distance for realistic detector, is just 4.05 nanosecond. For pines, it would be 40 nanoseconds, just slightly shorter. The difference between the travel of kaon and pine is only 50 picosecond. Well, the standard modern detector plus readout electronics have time resolution of an order of 10 nanoseconds, well, a couple of nanoseconds. They are fast enough to separate the different LHC bunches because the bunch crossing 25 nanosecond apart, but we need the resolution much better than 1 nanosecond to do useful job for time of flight measurement. Another consequence of that is the time of flight gives good identification at low momentum, as obvious from the figure at the right, and above 5 GeV you really need excellent time of flight time resolution. Let's recall a simple concept, how to measure time difference between two detectors. We can use simply the time of beam crossing at left to provide the start signal. However, due to magnetic field, tracks are not straight lines, so you need many hits to reconstruct track, and we need tracking detectors to determine actual path lengths. In reality, we have multiple tracks, which clearly would give rise to ambiguous solution. So our detector should be segmented in order to discriminate between different tracks and remove this ambiguity. This determines the basic layout for the time of flight hodoscopes made of scintillator bars, as shown at the right of the figure. Let's discuss performance of time of flight. The number of standard deviation to separate between two particles with different masses m1 and m2 is given by this formula. Clearly, the Uh, Time of flight works better if the distance between detector planes or between the interaction point and time of flight detector is large. It is given by d, and the denominator of this formula should be minimized, which works at very high momenta. You see p squared in the denominator, or you need a very good sigma t, which also enters in the denominator. Uh, well, sometimes combination of time of flights with DDX can help to remove ambiguities. You see the performance of various ionization detectors for Na49 experiment is shown at right. Now let's discuss ionization. As you have already learned, charged particles passing through matter can knock out electrons from atoms of the medium, and it will produce ionization. The energy loss is described by the Beta-Bloch formula, and which explains the dependence between ionization losses dAdx and velocity of the particle beta. And you see the ionization loss as a function of momenta for different particles at right: electrons, muon, pion, kaon, and proton. This dependence can be used to identify particles, particularly at low momentum, where you see the rapid variation in dAdx. The advantage is that we can use existing detectors, which are anyway needed for tracking, but we have to add to this detector an extra function which would allow accurate measurement of the charge. Let me also note that these techniques will all provide signals for charged leptons, electron, muon, as well as for hadrons, pion, kaon, and proton. But since the mass of muon is very close to the pion mass, they will not provide, DDX will not give a very good separation. Dedicated detectors will do much better job. Note also, if we plot DDX as a function of momentum, it has a lot of overlap regions between the different mass hypotheses, like shown at the right with a red circle. Indeed, you could achieve very good separation only at low momentum, and in order to improve this, in order to provide discrimination in the full momentum range, we have to use other detectors. Let me also show here the CMS results for DDX, and you see essentially that at momenta above few GeV, it is not possible to distinguish between different types of particles. So next methods I would like to discuss is transition radiation. Local speed of light in a medium with refractive index n is given by this formula, and if its relative performance V over Cp changes, a particle will radiate photons. There are three types of radiation. If you change the direction of V in magnetic field, for instance, you will produce synchrotron radiation. Change of modulo V passing through matter results in Bremsstrahlung radiation. And thirdly, change of refractive index of medium would produce transition radiation. Transition radiation is emitted whenever relativistic charge particles traverses the border between two media with different dielectric constant, since refractive index is proportional to the square root of dielectric constant. The energy emitted is proportional to the boost of the particle, hence this transition radiation is a particular useful for electron ID, in addition to the calorimetry. It can also be used for hadrons, but at very high energy. The energy emitted by transition radiation when charged particle crosses a boundary between vacuum and a medium with a plasma frequency omega p is given by this formula, where alpha is a fine structure constant. H omega p depends on the density of electrons in the material. For low Z materials such as plastic or e.g. polypropylene, it is about 20 electron volt. Hence, for 10 GeV electron, the gamma is about twice 10 to the fourth, so the delta E is in the keV range. The photon emissions at one interface has rather low probability, just 1%. So you need many layers of thin foils to be used in the radiator. And usage of low Z is important to limit reabsorptions of the radiation. Finally, radiation emitted in the very forward direction along of the particle direction. The angle of the cone is proportional to 1 over gamma. Therefore, photons will be seen in the same direction as ionization from the track. This is of clear advantage. Final method is the Cherenkov radiation. You have heard about that already, so you must remember that the Cherenkov light emitted with the angle, the cosine theta of which is given by 1 over beta n, and it is produced equally distributed over photon energy. That means that when transformed to a wavelength distribution, it must peak at very low wavelengths, at ultraviolet and blue. It is, for instance, responsible for the blue lights seen in the nuclear reactors. The number of photons detected in a Cherenkov detector is given by this formula, where again alpha is a fine structure constant, L is the length of the radiator medium, and epsilon is the efficiency for detecting the photons. There is a clear threshold for light production, since cosine theta cannot be larger than 1. Tracks with beta less than 1 over n give no light, and tracks with beta larger than 1 over n produce light. This principle is used in the so-called threshold Cherenkov detector, which are very useful to identify particle in a beamline, for example, with a very fixed momentum. And for instance, in a 50 GeV pion beam with some proton contamination, you could see at right that by choosing a proper medium with a suitable refractive index like neon gas, as shown here in this example, it can be arranged that pion will produce light, but the protons will not. The principle of this Cherenkov threshold counter is shown at the sketch in the bottom of the slide, and at the bottom right you could see this historical detector. Threshold counters just give a yes or no answer, but you can do more, and in particular it is important when your tracks have a wide momentum range. Then you could extract more information from the Cherenkov angle, not just use the threshold, but really measure Cherenkov angle. The Cherenkov cone can be imaged into a ring using a spherical mirror, as shown in this figure, and then you see the detector plane shown in red, and the radiator medium with the spherical mirror in the end of the radiator. Then the Cherenkov light can be reflected to the detector plane and form sort of circle, and measuring the radius of this circle, you could measure the Cherenkov angle, theta c. In the real experiment, in particular working at hadronic collisions, such as LHCb, for instance, many tracks will be seen in your detectors, and this will lead to many overlapping rings. And deciding which hit belongs to which track requires rather complicated pattern recognition. You see at the right the simulated events in one of the ridge detectors of LHCb. And there are various rings because LHCb ridge detector contains two radiators made of aerogel and which produce large rings, and small rings are produced in the second radiator filled with C4F10 gas. Most approaches rely on the use of track to seed the ring search. After transformation through the optics of the ridge detector, the track image will always be at the center of the ring, and the ring search then would correspond to the search for a peak in the number of photon hits versus radius from the track of the particle. And then separating two particle types using the signal from the ridge detector can be illustrated at right with the data taken at the test beam. Let's assume that the Cherenkov angle is determined with the resolution of an order of 0.7 millirad, and then peaks separated by 4 millirad, an angle would correspond to 6 sigma, very good separation. In general, the number of sigma in separating two tracks with masses m1 and m2 is given by this formula. It is inversely proportional to momentum squared and to sigma in determining theta, so it is quite similar to the expression for time of flight accuracy. However, in case of ridge, we have additional amplification factor 1 over square root of n squared minus 1, which is missing for time of flight. And for that reason, time of flight works only at low momentum when p squared is small. Here in Cherenkov light detectors, you could use this amplification factor and extend your accuracy of your measurement up to very high momenta. Adjusting the position of the cut placed between two peaks corresponding to kaon and pion, well, you could have a trade-off between increased efficiency and increased misidentification. This was studied in detail for the LHCb ridge system, and the performance of the ridge system in terms of efficiency and mis-ID for pion and kaon is shown at the bottom right, and this simulation is now very well confirmed with data. So now let me summarize what we have learned about identification of the charge hadron. There is a wide variety of techniques for identifying charged particles. Firstly, we can use transition radiation. This is in particular useful for electron identification because it is proportional to the boost. It can also be used for hadron ID at high momenta. Cherenkov detector, if you properly adjusted refractive indexes, they are very powerful at all momenta. And this is very useful detector for particle ID, probably the most useful. Ionization energy loss is provided by existing tracking detectors, but they should have the function of the charge measurement, and they usually work very well at low P. At high momenta, they almost useless. Time of flight provide excellent performance also at low momentum. However, with the development of faster photon detectors, the range of the time momentum coverage should increase. Now we are discussing time of flight measurement with an accuracy of 10-20 picosecond for other large detectors. So it brings me to the summary of my lecture for all three parts. Particle identification is a crucial aspect of most high-energy physics experiments, in addition to tracking and calorimetry. Short-lived particles are reconstructed from their decay products. Most long-lived particles seen in the experiment can be identified from their signature in the various different detectors. Distinguishing the different long-lived charge hadrons, pion, kaon, proton, is more challenging and usually requires dedicated detectors, and their identification is based on four main processes: time of flight, DADX, transition radiation, and the Cherenkov effect.